Good afternoon, everybody. My name is Silvia Spriano. I work at Politecnico di Torino in Italy, and the title of my talk is Metals as Biosurfaces in Implanted Medical Devices, Open Issues and New Strategies for an Improved Host Response. This is an overview of solved and open issues related to failure of implants, mainly orthopedic and dental implants. We can see that there are some almost solved problems, such as the formation of fibrous encapsulation and problem related to fracture toughness and fatigue strength. There is a problem that is the mismatch in modulus of elasticity between bone and implant, so the stress shield effect, that is partially solved. And there are some open issues, such as infections and chronic inflammation and wear of the articular prosthesis. I will not face the last issues, but I will make an overview of the others. So, we had in the history an evolution of titanium alloys and surfaces according to the different requirements. As first, the alloys were developed with tensile strength and fatigue strength high enough for the load of an implant and toughness too. So currently this is a solved issue. Usually failures are not related to materials, and if a fracture occurs, it is due to surgery procedure, to the design or manufacturing issues. As we told right now, there is a problem related to the stress shielding effect. The perspective is to use some beta titanium alloys with a slight lower elastic modulus with respect to the titanium 6-4, but the difference is not so relevant, so probably this will be not the final solution. And then the second requirement was fast osseointegration. At the moment there is a lot of products on the market responding well to this requirement, so with good osseointegration, obviously depending on the type of the bone where the implant is in. And some failures occurred in the past. You can see here an overview of different surface topography produced by different techniques, such as additive manufacturing or different coatings. In some cases we had some failure, like in the case of the sintered wires, but there are a lot of good choice on the market. So this is not such a big issue at the moment. And the next step, so for the future, is the development of multifunctional properties on the same surface. In the case of the permanent orthopedic implants, we need for sure osseointegration and then an osteoimmunomodulation with a proper inflammatory response, and then action against infections, like passive surfaces able to avoid the adhesion of bacteria, like antimicrofouling, or active antibacterial surfaces able to have an active antibacterial action to kill the bacteria on the implant and in the surroundings. In the case of temporary orthopedic implants, some issues are the same, but we have some more functions required by the surfaces, such as the integration with soft tissues in the case of transcutaneous implants, and in some cases an anti-adhesive surface able to avoid the overgrowth of bone. We have researches in our lab covering almost all these issues. I will give you an overview of some of these researches. As first, we developed a nanotextured titanium surface through a patent chemical treatment consisting in an acid etching and then oxidation in hydrogen peroxide. And the first result is a surface with a multi-scale topography. That means a roughness on the micro scale and then a second roughness on the nanoscale. You can see it in this SEM picture. And you can see here the AFM topography of the surface. You can see the micro topography that is in any case below 1 micron. That is the best, almost assessed as the best roughness for implant eye bone implant contact, avoiding the risk of fatigue fracture. And you can see also the nano topography on the nanoscale. Concerning the chemistry of the surface oxide layer, we have, because of this treatment, a higher amount of hydroxyl group, a very high density of this group on the surface. And we can see from the zeta potential titration curve that there we have a shift, a very relevant shift of the isoelectric point with respect to the untreated surface. And this means that the hydroxide group has an acidic behavior, so it is deprotonated easily. And this plateau shows us that we have the groups are completely deprotonated at any pH higher than 5. This means that both in the inflammation condition and in physiological condition we have a negative surface on the negative charge on the surface due to the presence of the deprotonated hydroxide groups. And because of this, the surface has a very high wettability, so it is able to attract the physiological liquids. This is a dental implant with this treatment, and you can see that there is an attraction force for the liquid. And we have an bioactivity, that means the ability of inducing precipitation of hydroxyapatite during in vitro test, and so hopefully also in vivo. You can see here a pretty nice layer of hydroxyapatite on the surface of the treated titanium alloy. And concerning the response by different cells, we can see here a high adhesion, differentiation, proliferation and differentiation of the osteoblast. And here we can see the treatment applied to a coating made of spheres of titanium, and you can see a high adhesion of fibroblasts that is quite higher than on the untreated surface. So the surface is suitable both for bone contact and soft tissue contact. And this is very interesting. There is a very low amount of macrophages, adhesion and proliferation on the surface. So the surface is also able to induce a control of the inflammation response. And it is also of interest that on this surface we have a reduced bacterial adhesion, so we have a passive action against bacteria. We have no active antibacterial agent on the surface, but because of the topography and the chemistry, we are able to reduce the adhesion of different bacteria. And further development is the functionalization with an active antibacterial compound. You can see here that this surface can be obtained on several real implants, dental implants, orthopedic implants, also produced by additive manufacturing or coating made of spheres. So the patent has been developed and it is almost ready for industrial application. And we can also have an improvement of the surface because thanks to the presence of the hydroxide groups, we can make a functionalization of the surface. So we can add some biomolecules. For instance, we tried with polyphenols extracted from black and white grapes. And polyphenols are auto-fluorescent, so you can see here a pretty nice coating of polyphenols on the surface. And by XPS we can also define the type of the chemical bond between the polyphenols and the surface. And we observed that in some cases we have an improvement by using calcium ions during functionalization, and so we have a link that is a strong chemical bond through the calcium ions. And we tested the release of the polyphenols. We can see that we have some release in some hours, but we have also a very long life of this coating for up 1 month at least because of the strong chemical bond. And polyphenols have a proved activity in order to enhance the adhesion of osteoblasts and an anti-inflammatory and radical scavenging activity, so they are able to add these properties to the surface. Okay, then we can move to another. Oh, here you have some papers if you want to go through this research. And another type of treatment is through E-beam or laser, and in this case we can obtain some grooves on the surface. And these grooves are very effective in order to enhance the adhesion of fibroblasts and to orient the fibroblast in this direction through a contact guidance effect. So this type of surface is useful for temporary orthopedic implants, and it is able to enhance the integration with the soft tissues. And we can also see that because of the laser or E-beam treatment, we can get again a nanostructure of the surface with these sharp steps. And we have an anti-microfouling effect, so we gain a passive action against biofilm formation. You can see here the contact guidance effect. So every time you have these grooves on the surface, you have a high alignment of the fibroblast. If you have just the polished surface without any groove, you have no alignment. And if you treat the surface with the E-beam or laser and then you polish the surface, you reduce again the alignment because you are removing the grooves. So the alignment is strictly related to the presence of the grooves. And there is also an effect on the dimension of the groove. The better result is with grooves wide around 10 microns. If you have larger grooves, the effect is lower. And here you can see on different titanium-based materials, the beta titanium alloy or pure titanium, that there is this anti-microfouling action. So there is a reduced amount of bacteria because of the steps on the surface. And this can be explained considering that the bacteria have a stiff membrane and they are very large in dimension, so they want to maintain their shape, and it is difficult to do this on such a surface, so there is a reduced adhesion on the nanotextured surfaces of the bacteria. And some papers about this topic if you are interested in this. Another story, another surface is is through deposition of keratin nanofibers. Keratin nanofibers are able to enhance fibroblast proliferation. So again, they are of interest for temporary orthopedic implants in order to enhance the integration with the soft tissues. And again, we can get a contact guidance effect if you have oriented nanofibers. And we can dope these nanofibers with silver ions. So in this case, we can get an active antibacterial effect. And you can see here some random or some oriented nanofibers of keratin extracted from some waste in the industrial production of wool. And you can see here that you can have a random orientation if the fibers are random, or you can have an orientation of the fibroblasts on the oriented fibers. And if you dope the fibers with silver ions, you can see a pretty nice antibacterial action. And in any case, you have a biocompatible surface without any cytotoxicity. Okay, so we can come to some conclusions. The mechanical and osseointegration requirements of orthopedic implants are almost achieved. The new goal for biomaterials and titanium surfaces is a multifunctional action. So we need immunomodulation, we need a low risk of infection, or through a passive or through an active strategy. And we investigated a surface, useful in the case of permanent orthopedic or dental implants, able to induce the precipitation of hydroxyapatite, so it is bioactive, able to enhance osseointegration, able to induce immunomodulation with a low amount of macrophages, so with an anti-inflammatory action, with a low adhesion of bacteria. And it is obtained through nanotexturing of titanium alloy through a chemical treatment in fluoridic acid and peroxide hydrogen. We can have a further improvement if we functionalize this surface with some biomolecules such as polyphenols. And in the case of transcutaneous temporary implants, we developed different surfaces made with oriented grooves on the surface through E-beam or laser structuring, or with a coating of keratin nanofibers. In both cases, we can obtain a good interaction with soft tissues, with fibroblasts, and an anti-microfouling passive or an antibacterial, so an active action. This last one in the case of doping with silver ions. Thank you very much for your kind attention. This is my email, so I will be very pleased to discuss with you if you are interested to go through these researches. Thank you again.